So we'll build these affiliation networks, flock networks, based on who is seen in flocks together. So we can get a network like this. This is one of our seasons. It's based on approximately 400 individuals, ranging from single individuals to flocks of 8 birds or so. And so, right, and I should mention these flocks are very dynamic. They're very temporary. And so they're foraging flocks. They go through kind of space. Individuals join, individuals leave. And so what we define as a flock is basically what we can see in one time period. But as Damien mentioned earlier, in a lot of these cases, the flocks are pretty easy to define if you're watching carefully. There's a group of birds here and a separate group over there. Okay, so we can investigate kind of the structure of these networks. So one way we can do is using some algorithms to try to identify some clusters of individuals that flock together more often than not. We can map these communities onto space. So obviously, there's going to be spatial structure in these communities. So here, these are just kernel home range estimates. In the shaded areas, kind of the core areas, and the outlines are more of the general home range. It's just the aggregate home range of these members in each community. So you can see they overlap a lot, but they are kind of discrete. Another thing we can do is, like many of you guys are interested in comparing these across time. And so following on the discussion of what's a relevant time slice, I think it's kind of helpful here is that we have a pretty well-defined time slice biologically. Everyone leaves, everyone comes back and have to reform these networks. So we're pretty comfortable aggregating this kind of on a yearly basis. And again, there's some turnover in individuals. Okay, so of course, a big challenge is to try to tease apart spatial and social factors. Whether or not we can really do that completely, I'm not so sure. But basically, the question is, do birds really have kind of preferred flock mates? Or is it just that they're flocking randomly and that these home ranges are aggregated kind of non-randomly in space? And so a couple of approaches I've played around with. One I might call kind of spatially informed null model. So you take the home ranges of every individual, and you use that to model what the network might look like if flocks were random aggregations of birds that share the home range or the spot where the flock was observed. But I'm not going to talk about that today because it's takes longer to explain. And then another approach is kind of the statistical model approaches, like a couple of earlier talks touched on. Here I'm going to use just a multiple regression quadratic assignment procedure. I often just call them network regression for people that aren't familiar with them. So using spatial versus social factors as covariates and see controlling for space, if we can tease apart any other factors that are important in structuring the network. So just a simple illustration. Obviously, the degree to which home ranges overlap explains a lot of who they flock with. If they don't share any part of their home range, they can't flock together. If they share almost all of it, they are going to find each other more often. So, another factor that turns out to be important is how much the pair of birds flocked together last year. Okay, this is just, I'm not doing any statistics on this. It's just a kind of plot to illustrate that if you flocked a lot together last year, you're also more likely to flock together this year. And so taking these two as covariates, I run a MRQAP, and you can show that they're both important, right? So both previous year's association is important, as well as home range similarity. And that explains a pretty good amount of the variation in how much they flock in the current year. And just to remind you, so what we're kind of hinting at is the social preference based on experience from at least months ago, kind of reform and help shape the network. And so if we're looking at it from kind of a community structure perspective, we can look at the community structure of the network in 2 years and then see. So we tend to see similar community structure across years. So we always get kind of these 3 communities. Sometimes we get some other individuals that these 3 guys tended to hang out over here, and we didn't pick them up the previous year. But generally, we got 3 communities. They break down and around the same areas. And we can see if birds that were in this community come back to the same place or associate with the same guys next year. When we do that, we always see that that's very true. So in this case, 95% of the time, birds that come back flock together again the next year. We can do that for the next time step. You get 100% of the birds come back to the same community across years. And so I've done some other analyses to look at these dynamics that I won't go into detail here today. But just to wrap up what I've told you, what we get is these kinds of social clusters that arise in pretty small areas. I think earlier I totally skipped over the spatial scale of this, but this is about 300 meters by 300 meters. If you like an American, it's like 2 foot to 2 football fields or something. American football fields. Okay. There seems to be some kind of across-year social effects or fidelity among flock mates, which I find, excuse me, really interesting in these kind of migrant systems. And then we see the stability of community structure across years. One thing that I'm not ready to present yet because we're still kind of working with the data is to hope to do some experiments to show that the spatial proximity actually matters. So we've been taking birds that we catch in certain distance apart versus pairs that we catch in the same place, put them in an aviary, give them one food. We call these gladiator contests and just see what they do. And as we predict, if you take 2 birds far apart, they fight a lot more than if we catch them from the same place. And so we're starting to put together a picture of how this social structure actually matters in terms of behavior. Okay, but for the rest of this talk, I wanted to kind of focus on some thoughts that I've had observing the system. And one is this, what I'll call a puzzle regarding how we get community stability in these kinds of systems, because there's a lot of mortality across years. Each community, or the population overall as well, loses 30 to 50% of its members across years, and new members join the community. Immigrants, new recruits, and so after just these 2 time steps, we see 60 to 80% of turnover. And so although these communities kind of exist across years, the individual members are not the same. And you can see across time, you're just perpetuating the same structure or same communities a long time. I kind of, as an analogy, I like to think of like a French club in your high school or something, right? So you have individuals that form a group, every year, new ones are coming in, and some are graduating after 4 years. You still have a French club, but no one's the same. And so I'm interested in kind of how these stability can arise in natural systems. And so, and communities can outlive individual members. And so I think what we really need is a kind of more general model or way of integrating demography and other ecologically important factors to network structure to really tie what we're studying more into ecology, I think. Okay, so just one example question: how does social structure remain constant despite the fact that the population has turnover? I think just to throw out a couple of key parameters, I think that are important. Obviously, the turnover rate, mortality, and recruitment rates. How long social ties last. So borrowing Tanya's vocabulary from yesterday, maybe duration of ties. From a behavioral perspective, I think it has something also to do with kind of social memory or something like that. And then how new recruits become integrated into the existing communities or not. And so I've toyed around a little bit with some simulations, and I think it's completely inadequate, but I think it's just interesting to think about. And so consider a system that has two discrete communities at the beginning. Is this still?
Still on?
It's still on, okay. And so here, I'm going to say 10% of, we randomly pick 10% of the individuals to die off. The same number of individuals come in to replace, and then they might get integrated into communities in different ways. So simple example, new recruits begin to get associate randomly in the population. If you do that very predictably, community structure disintegrates. If you plot that across time, modularity across time, if you get 10% mortality, it takes about 10 time steps to get to kind of a random level of community structure. If you consider a scenario where communities are closed to new members, right, you can maintain high modularity. This is kind of the starting point, modularity. You can have very discrete communities, but each of those communities are going to die off as its individual members die off. And so you get fragmentation and smaller communities. But if new recruits are allowed somehow to integrate into existing communities, then you can perpetuate kind of the existing social structure and maintain kind of the same level of modularity. Again, this is kind of just the beginning, but I think these types of models will be really useful to start understanding how ecology actually matters. Okay, and then just another version of this, if I alter turnover rates, but so I'm taking the model where individuals are allowed to integrate into communities, but there's different turnover rate. A lot bigger proportion of individuals die off. You get, after a few time steps, these are means of about 100 simulations each, you get, it's hard to maintain community stability when more than half your individuals are dying off, right? So what I'm just proposing is, I think, a good step that we could take is to start understanding these types of dynamics, and has a lot of implications. So understanding population dynamics, a lot of things ecologists are really interested in, might tie into things like allele effects or how the population size might destabilize social structure. Obvious implications for evolution of cooperation, how you can get stability in a system that's always changing. I think there's also interesting implications for cultural evolution. So if you start thinking about these communities as not just individuals, but some characteristic, like, so thinking about birds, dialects of songs or something that's learned and transmitted, not just vertically, but kind of obliquely in your neighborhood. These kinds of, the stability of social structure might influence how cultural evolution might occur. And I think there's a lot of other implications. So these are kinds of ideas that I've been tossing around in my head, and I wanted to share them and hopefully get some feedback. OK, so good. That was pretty quick. Some thanks, my collaborators again. Dave for introducing me to networks, and now he can't get rid of me. With any kind of these field work, we have a lot of undergrads. All this was done on the campus of University of California, Santa Cruz, so it's a great system because just get perpetual teams of undergrads that go between classes and observe flocks. So thanks.